trying to say all week, but we've been delayed because of the quizzes that we've had and the surprising results that you guys have given me. So we're going to talk today about potential energy, and then we're going to talk about conservation of energy. So I've tried to slip this in, but it's always been towards the end of class. These are things I should have said the whole time, but what I have to teach you today is a little bit challenging. So not that it's hard, it's challenging because of the concept, but once we get the concept down, once you have the definitions down, it says it's stored energy. Have to know isn't so terrible. So I want to explain some of the things that are being said here. Now, there are lots of different kinds of potential energies. In all forms of potential energy, the energy is being stored for later use. The word potential here actually means something different than the way I've been using it in the past. Can't even spell potential energy. I'd like you to know it as the potential to do work. When we talk about potential energy, because we're dealing with mechanical energy, in every form of potential energy we will discuss, we're talking about the potential for your object to do work. The simplest form of potential energy we're going to discuss is gravitational potential energy. And in fact, in this class, we'll only have two forms of potential energy this semester. We're going to have gravitational potential energy and elastic potential energy. I'll be using an uppercase U as a symbol for potential energy and a subscript of G for gravitational potential energy. And I'll use an uppercase U with a subscript of E for elastic potential energy. Also known as spring energy. Now, this idea about potential energy isn't fictitious. The reason we study energy is because energies in one discipline are the same as energies in another. There are lots of other forms of potential energy, such as chemical potential energy, nuclear potential energy. These are all different forms of potential energy, and I could list a couple of more, but the point I want to make to you is that these are all forms of stored energy. These two, however, are mechanical in nature, which means they're related to movement. The word mechanical means movement. These are not. These are more thermal. The energies that are related to chemical and nuclear potential energy usually give you some kind of thermal energy. They get something warm or get something hot. That's generally how you know where you have energy when you're in chemistry, because you measure it with temperature. We've kind of already talked about that. But for us, since we're dealing with mechanical forms of energy, most of our forms of potential energy will deal with position. There's something about the position of the object that matters. Now, the simplest concept for me to kind of cover is gravitational potential energy. It's the easiest one for you guys to kind of wrap your heads around. Not that either wrap your head around, but it's one where you've already kind of know things that are going to happen. Just imagine I have, a ball. If I lift the ball up and release it, there's not a person in the room who doesn't already know that the ball is going to fall back to the ground. And by the time it makes it back to the ground, it's going to have some velocity. Simple idea, correct? Now, the question I want to ask you is, if I lift the ball up to here, and this is condition A, or I lift the ball up to here, and this is condition B, which one will be traveling faster when they make it to the ground? This is not a hard question. If you don't know the answer to this question, then we have to have a chat. Right? But if I drop both of these, I'm pretty sure B will be traveling faster. It has a longer distance to fall, right? Gets pulled on for a longer period of time, gets accelerated for a longer period of time. B will be traveling faster than A. If I was to consider this height, let's just say it's 2 meters, and this height is 4 meters. There's nothing special about the space there. There's something special about up here that's different than up here. But if I drop something from up there, we know that it'll be traveling faster when it makes it to the ground. Now, I said to you that the idea here is that if something has potential energy, it has the potential to do work. Let's evaluate that. If this isn't a ball, what if instead it's a hammer? If you're trying to drive, say, a nail into a plank of wood, and you lift the hammer back this far, and just let gravity pull it down, it will probably drive the nail a little bit into the wood. Would you agree that if you lift the hammer up higher and just let it drop, it's probably going to drive the nail further into the wood? Yes. The potential to do work is greater because we changed something about the hammer. This is the basic concept behind potential energy. It's a very straightforward concept. So when we talk about potential energies, we're talking about the potential for the object to do work, which could be as simple as applying a force to a nail or converting that energy to to kinetic energy. Remember, the potential to do work can mean one of two things. This side is applying a force to an object. This side is a change in kinetic energy. Work can be either one of these. So if something has potential energy, that means it either can do work when it uses that potential energy, or it could change its own kinetic energy. That's what we really talk about when we talk about potential energy. Unfortunately, like everything else in this class, potential energy has definitions that have to be observed. I wouldn't normally spend any time at all on this portion of our conversation. I usually skip it completely, but it's turned up on the AP exam a couple of times. So it's worth having this conversation. There is a specific definition for how you change something's potential energy. A very specific definition. We say that we define the change in potential energy, which means 3 lines for our equal sign. And we are defining this quantity as minus the work done against a conservative force. This is how we define a change in potential energy. This concept might be difficult for us. Like, why is it defined this way? And I want to show you why it's defined this way so you get an understanding, but what we're going to do is we're going to derive gravitational potential energy. Now, first, you have to know what a conservative force is. There's no good definition here. I'd love to tell you that I have a perfect definition, but even the definition in your book is garbage. A conservative force is a force that conserves energy. That's pretty circular logic, doesn't tell you anything. And it's the definition in the book, but a conservative force is a force that conserves energy. It's a waste. I will not ask you that question on any test. I will, however, say that a conservative force is path independent. That is important. That's worth asking about. Conservative forces are path independent. That's going to come up. So that's worth highlighting, box around it, kind of thing. So we've already tried to investigate this, and I've already tried to indicate it to you. If I lift something upwards, I am somehow giving that object potential energy. That's what I've been saying this whole time. I used the ball, the hammer as my examples. Now we're going to do the mathematical part of this, which means I want to calculate the work done lifting something. I want to calculate this work, so just need something to lift. Here's a book. We're going to lift the book. Now, here's the thing. I'm going to lift the book from here to here. Now, I'm trying to calculate the work done by gravity while I lift the book. I'm going to talk very slow and deliberate. It's worth writing these things down, and I don't want to, because I really don't want to answer some of the questions you're going to ask later. So I want you to write the answers down right now. We are lifting the book. So that means we're going to displace the book this direction. This will be the displacement of the book. We're not talking about the work I'm doing. We're talking about the work against the conservative force. So it's not about my upward lifting force. It's about the force of gravity, and the force of gravity is acting downwards on the book. This is the work done against a conservative force. But more importantly, it's the work done by that conservative force while you're working against it. So I lift the book upwards, which means the force I'm applying times the displacement times the cosine of the angle between them is going to start with mg. That's the force of gravity acting on the book. The displacement is going to be whatever height I lift the book to. And I'm lifting the book upwards, but the force of gravity is downwards, so 180 degrees. Don't be the person in 10 minutes to ask why it's 180 degrees. The book is moving upwards, but gravity is pulling downwards. That's where the 180 comes from. We good? All right. Now, that's it. That's the work done against gravity, which is going to be minus mgh. And when we're done, the book is now up here. Now, nothing's really different about the book, except that it's higher than it was before. But because we did this work, we lost energy. That energy went into the book. Because by definition, right here, by this definition, the change in potential energy of the book is equal to minus negative mgh. Negatives cancel out here, and we say that the change in gravitational potential energy is equal to mgh. This is how we calculate gravitational potential energy. Now, I want you to, I'm not going to write this as notes, or at least I'm not going to write these words down, but nothing is different about the book. There's no energy stored in the book. There's energy stored in the fact that the book could be brought back downwards by gravity. This energy is stored in the connection between the earth and the book. I want to be very clear about this because they're going to try and ask this question on the test. There's nothing in the book. The book can have kinetic energy, and that's it. When it comes to mechanical forms of energy, kinetic energy is about the book. It can be moving. But potential energy has to involve something else. In the case of gravitational potential energy, this is an interaction between the book and the earth. So there's going to be, questions on the test that are going to try and probe this, but nothing is different about the book. The energy is stored in the fact that the book and earth are now separated by a larger distance. And because of that, we could get that energy back if the object were to fall back to the earth. So this energy doesn't exist on its own with the book. It exists between the interaction between the book and the earth. I've said it 3 different ways. I've made sure to throw the word interaction in there very clearly, and that 2 objects are required for there to be potential energy. In the case of gravity, that object is going to be the planet and the other object. Now, in practice, this is a little bit more straightforward. When we talk about potential energy, we're talking about the potential for the object to change its height. So let's say this is my desk. There's a variety of items on my desk. Now, I don't expect my coffee cup to fall off my desk. I don't expect it to, but it is precariously close to the edge of the desk. Would you guys agree? Does the coffee cup have potential energy? Now, this statement sounds easy, and I'm directing you to like how to find it. For example, if I was to ask you to calculate how much potential energy the coffee cup has, what would you need in order to do so? It's in your notes. It's right in your notes right now. What are the things that you would need? Somebody said one of the words. Mass. That's one of the words. I would need the mass of the coffee cup. What else would I need? Yes, sir? Height of the table. How many of you agree height of the table? I think that's not unreasonable. And probably G, right? Now, here's where I want to help you understand why this is a more cumbersome conversation and why I'm going to rewrite our definition just a little bit to help us. If the cup never falls off the table, does it really have potential energy? I mean, look, I'm not changing the height of the cup right now. I didn't change the height of the cup, so I never changed the cup's potential energy. But what are the chances it's going to fall off the table now? You understand that it's no longer perched precariously towards the edge. Did I really change anything about the cup? No, and worse, where do I begin talking about the potential energy for the cup? Somebody brought it upstairs. If I really want to talk about potential energy, do I start from the ground outside? Well, that would be pertinent. Here's the thing about potential energy, and this is the thing that you need to write down. This is the important concept. This is what you really need to know, and this is why I'm kind of refocusing all of you really fast. Potential energy is about the potential to do work. That phrase. It's a construct that we made. So here's what I want you to write down. The height depends on the lowest attainable place that the object could reasonably make it to. In our problems, in our work, potential energy is about the lowest attainable place that the object could make it to. There are no absolutes here. The cup never has an absolute amount of potential energy. Potential energy is a useful concept that we use to solve problems. I said it's not something about the cup. The cup never has the energy. Because, like I said, there's downstairs, right? The cup had to be brought from downstairs. What if somebody went outside and just dug a big hole? Would that suddenly change something about the cup? No. So nothing has changed about the cup. The thing is, in any time that we sense it's useful for us to use potential energy, what you need to look at is where is the lowest point the object could travel to? The lowest point the object could travel to, I call the reference level. We use potential energy in situations where objects change their height. Because of that, consider the possible reference level. That's what potential energy is really about. It's not about an absolute. It's about changes. And in this case, it'll be changes in the height of the object. Let me give you a for instance. We've seen plenty of problems where I've asked you to figure out how fast something is going when it makes it to the bottom of the ramp, right? More than enough times. What if this is our ramp? 2 meters high, I place a ball here, and I want you to figure out how fast it's going when it makes it to the bottom. I put K there because I'm trying to point you towards kinetic energy. In the past, this would be a problem that we would not be able to do for a number of reasons. The first one being, is the acceleration ever constant? If we look at the beginning, it's very steep. If we look here, it's not as steep. This is not a straightforward incline where the acceleration is going to stay the same all the time. I would not be able to calculate the work done. I would not be able to calculate the acceleration. I can't use what we've talked about so far this year to solve this problem. However, I said something very important earlier in our conversation, and that is potential energy is path independent. All it cares about is changes in height. I'll say that again because that's the emphasis I want to make. Potential energy is path independent. All it cares about are changes in height. So let's say this whole thing is on a table. The ground is down here someplace. And I ask you, how fast is the ball going at the bottom of this ramp? Well, this problem might not be as hard as it seems. I want to show you how to solve this problem. I need to do a little mathy math stuff in the beginning, okay? So here's the mathy math stuff I want you to think about. And I'm going to produce a result here. You'll never have to derive this again, but I'm going to produce a result, and that result is the most important thing for the discussion today, okay? First, I said that the change in potential energy is equal to minus the work done. In the case of this ball rolling down the ramp, that work is going to be equal to the change in kinetic energy of the ball. Good so far? Change in means U final minus U initial. I'm dropping the G for right now, so I can put these subscripts there. Is that okay? The other side, because there's a negative there, it's negative K final minus K initial. So here's what I want. I want to put all the initials on one side and all of the finals on another. Everybody understand? So I'm going to distribute that negative sign. I'm going to move this over to that side and this over to that side. If there's no work done outside your system, the energy before an event occurs is equal to the energy after an event occurs. This is called conservation of energy. I'm going to say it another time. If there's no outside work done, honestly, no friction or you pushing on the ball, if there's no outside work done, and all we have are conservative forces. If there's no outside work done, and all we have are conservative forces, the energy before an event will have to equal the energy after an event. Everybody got it all down? So I want to explain how this works. It's so easy once you catch it. An event is going to occur here, right? The ball is going to roll down the ramp. That's our event. The initial state of the ball is up here. This is the initial state of the ball. It's at the top of the ramp. This is the final state of the ball. It's at the bottom of the ramp. What I just proved to you says that if we add up the initial amounts of energy and we add up the final amounts of energy, those two things have to be equal. So if I add up the energy here and I add up the energy here, those two things have to be equal. Now I have to be careful. Our version of gravitational potential energy is based on the idea that there is a reference level, and we need to be considerate of the reference level. So if I tell you the table is 2 meters tall and the ramp starts 2 meters above the table, what should I use as my height for my potential energy at the start? Should I use 2 or should I use 4? Now, the answer is, it doesn't matter. Pick a reference level and stick with it. I would probably want to use 2 and say that my reference level is the table. That's the lowest point the ball can make it to. So that's what I would want to do. But it's an arbitrary choice. If I chose to make this 4, that's fine. It just means that when the ball makes it to the table here, it's still 2 meters above the ground. You pick a reference level and you stay with it for the whole problem. But if you want a hint on how to solve these problems, choose the lowest point the object is likely to make it to. I'm going to choose the table, and I'm going to say that this is 2. By doing that, when it makes it to the bottom of the table, the potential energy is now 0. It's on the table. That was my reference level. Now here's the thing. If the ball wasn't rolling, if I just sat it on the top of the ramp, it has no kinetic energy at the start. So all of the energy at the beginning all that energy is potential. At the bottom of the ramp, all that energy is going to be kinetic. And the best part is, I don't care what happens in the middle. It doesn't matter. The gravitational force is path independent. So whatever happens in the middle doesn't matter. All I have to do is set these two states equal to each other. And I hope you see something important here. I don't have to give you the mass of the ball. Do you guys see that too? That won't always be true, but if all I'm asking about is the velocity of the object, apparently the mass doesn't matter. Have you ever been asked what your mass is when you got on a roller coaster? They don't need to know. This is a roller coaster. That's how all roller coasters work. Any roller coaster with a lift chain that's going to lift you to the top of the ramp. The most dangerous part of that roller coaster is the lift chain. Once you're up on the roller coaster, gravity does everything else. You're fine. The biggest fear that all roller coaster operators have is the lift chain failing. That's the most likely part of the roller coaster that will break. That's why you hear that clickety-clackety noise. You guys know what I'm talking about when you're being lifted up? That's the safety mechanism to make sure that not if, when the chain breaks, the cars don't roll back into the loading house. Because there's usually another car there, right? Loading people onto the next one. That's the most dangerous time. That's where all accidents have really occurred with roller coasters. The Hulk is famous for failing to launch up the lift hill. It's a launch roller coaster. In fact, there was one summer where it was failing about once a day, where it would launch, people would make the first hill, and it would roll backwards. And so they've had to take it offline for a year to rebuild the safety mechanisms to prevent that. All right, so let's consider a test case for you guys to try something, okay? Let's say it's cold out. Let's say you're a person who likes to go skiing. So you up here push off with an initial speed of 1 meter per second on a slope that is 10 meters high, assuming there are no external forces due to friction. How fast will you be going at the bottom of the slope? Truthfully, I don't think you need me for this at all. I think if you paid even a little bit of attention, you probably know what to do. You're going to take a look at what's happening at the start and what's happening at the bottom, and set them equal to each other. If you followed along, you can do it on your own. But I have some students who can't do it that way. They need to be spoon-fed this. So I'm going to tell you what you should do if you need to be spoon-fed. So if this is you, you pay attention today. I'm going to list out the possible forms of energy that we have. It's a long list, 2 things. I'm going to list them at the top. I'm going to list them at the bottom. And any state in between. So I might ask you about the middle here in a minute. But I'm only talking about the top and bottom state for now. After that, the thing you should ask yourself, go through each form of energy. Is the object above the reference level? If the answer is yes, it has gravitational potential energy. Is the object moving? If the answer is yes, it has kinetic energy. That's it. Go to the next state and ask the same questions. When you've completed it, set one state equal to another state. So I'm going to perform this. At the top, is my object above the reference level? Yes. I think the clear reference level is the bottom of the hill. It has gravitational potential energy. Is the object moving? Yes. I was given an initial velocity of 1 meter per second. I'm done with this state of the problem. Move to the next state of the problem. Is the object above the reference level? No. It's at the lowest point in the problem. It has no gravitational potential energy. Now here's the thing. Do you know if he's moving or not at the bottom of the slope? You don't really know. But you have to ask yourself, where would that energy go if it wasn't into kinetic energy? You follow what I'm saying? The energy has to go somewhere. So if there's nothing else to take that energy, all that energy must be kinetic, which means, yeah, he's probably moving. And actually, he's probably moving pretty fast. Once you have identified the forms of energy in 2 states of the problem, you set them equal to each other. I never gave you the skier's mass. In this particular example, you don't need it. If I did ask for an amount of energy, you would need the mass. But I didn't. I asked for the velocity of the skier at the bottom. So there's a mass in every term. I'm going to cancel them all out. I'm going to plug in 10 for G. And I get 201. Or I'm sorry, square root of 201. That's pretty fast, actually. This is why skiers get killed. They go fast, they hit trees, trees don't move. They have to you guys who have skied before, you know that, right? Yeah, don't hit the trees. Hit the other people, but don't hit the trees. Do me a favor, you need to practice. So let's say this is the point where they're 4 meters above the ground. How fast are they going there? This is your practice. You should be able to do it. Super simple. Follow the same procedure. I want to see what you can do, because then we're going to start, adding stuff.